Okay, this is algebra. This is the continuation of the previous lecture, lecture 19. I'm going over some of the homework problems, which I'm giving you a few more dates officially. They're due next Wednesday, on Wednesday, which is April 12th. And let's look at number 5, which we had discussed a little bit in the first part of this lecture. We're looking at symmetries of the square, or we want to show that the symmetries of a square can be represented by a set of matrices. So what are the matrices? We have the rotation matrix, R theta, which is a 2 by 2 matrix, cosine theta, sine theta, minus sine cosine theta. And in the plane, if you take a vector v and you apply r theta to v, you get the vector by rotating v by an angle theta. So applied to any vector, r theta of v is the vector you get by rotating your vector v by an angle theta. And rotations have the following very nice property. If you take two rotations, rotation by an angle theta and rotation by an angle mu, that's the same as rotating by an angle theta plus mu. Because if this is rotation by an angle theta, and this is rotation by an angle mu, when you put them together, you've rotated this vector a total of theta plus mu. And you can prove this just by multiplying together the two rotation matrices and using the addition formulas for the sine and the cosine. So the rotation matrices are these matrices for any angle theta, measured always in radians, and it satisfies this very nice property. We had 4 other matrices that we considered. The matrix J, which is 1, 0, 0, minus 1, that has the property that if you take the vector v and you apply j to v, you get the vector by reflecting your vector through the x-axis. So this is jv. I take the vector, reflect through the x-axis. So this is reflection through the x-axis. And we looked at the matrices you get as follows. Suppose R is rotation by pi over 2 radians, or 90 degrees. We saw that we computed the matrices Rj, R squared j, and R cubed j. So, for example, Rj, so what is R, which is rotation by pi over 2, that's cosine pi over 2, sine pi over 2, minus sine pi over 2, cosine pi over 2. But the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So R is this simple matrix, 0, minus 1, 1, 0. So Rj is 0, minus 1, 1, 0, times j, which is 1, 0, 0, minus 1. If you multiply them together, you get 0, 1, 1, 0. So Rj applied to a vector V, we always write V. I'm going to write my matrices as column matrices. V is xy. So this is 0, 1, 1, 0 applied to xy. That's yx. And in the plane, what does that correspond to? You have the line y equals x. And if you take the vector xy, that's reflection through this line. This is the vector xy. When you reflect through the line, you get the vector yx. So what we have is the following. J is reflection through the x-axis. Rj, which is the matrix 0, 1, 1, 0, is reflection through the line y equals x. I also want to calculate r squared j and r cubed j. So r squared j is r times rj. R, let's remember, is 1, 0. Sorry, R is 0 minus 1, 1, 0. And Rj is 0, 1, 1, 0. So this is the matrix. If you do your matrix multiplication, minus 1, 0, 0, 1. And so r squared j of a vector xy is minus 1, 0, 0, 1 applied to xy. That's equal to minus xy. So if you take the vector xy, it gets moved to minus xy. That's reflection through the y-axis. So r squared j, which is the matrix minus 1, 0, 0, 1, is reflection through the y-axis. And what about the third matrix I want to compute? R cubed j is r times r squared j. Again, r is 0 minus 1, 1, 0. And r squared j, I just calculated, is minus 1, 0, 0, 1. So that's the matrix 0 minus 1, minus 1, 0. So r cubed j of a vector xy is 0 minus 1, minus 1, 0 times xy. That's equal to minus y minus x. So if this is the vector xy, that gets sent to the vector minus y minus x. That is exactly reflection around the line y equals minus x. So r cubed j, which is the matrix 0 minus 1 minus 1, 0, is reflection through the line y equals minus x. So I've calculated 4 matrices and then another 4 matrices. We have rotation by pi over 2 radians. So we have r squared, r cubed, and the identity. And then each of those times the reflection j. And we end up with 8 matrices. We have the identity, r squared, r cubed, and then the matrices I just calculated, j, rj, r squared j, and r cubed j. So let's call this set of 8 matrices G. And I want to show that these are very explicitly the symmetries of a square. So I'm going to write a square, but I'm going to write it in this form. So let's say this is A, B, C, D. These are the vertices of a square. And what happens when I apply r squared, r cubed, j, and so on? If I apply these different linear transformations to the square. So if I apply r, that's rotation by pi over 2, I get A, B, C, D. If I apply r squared to the square, I rotate it by around the origin, right? I'm rotating it. A goes to here and then goes to here, A, B, C, D. If I apply r cubed, if I rotate it again, A comes down from here down to here. So here is my A. And of course, if I don't rotate it at all, if I just apply the identity, it doesn't change the square. So applying r squared, and r cubed to this square, I get this, this, or this. What happens if I take the square A, B, C, D? Again, this is the square centered at the origin in the plane and drawn like this. If I apply J, what is J? J is rotation, is reflection through the x-axis. So A and C don't change, but B and D are interchanged. If I apply J squared to the square, what is J squared? Let me go back and check. Sorry, not J squared. If I apply RJ to the square, RJ was reflection through the line y equals x. Here's the line y equals x. If I reflect through that square, this becomes AD, and this becomes BC. R squared J, R squared J is reflection through the y-axis. So if I take this square and I reflect it through the y-axis, B and D don't change, but A and C are interchanged. And finally, R cubed J is reflection through the line y equals minus x. So if I take my square and I'm reflecting through this line, AB on top get moved down here, and CD on the bottom get moved up there. And so each of these linear transformations, or each of these matrices, is a symmetry of the square. The set of points in the square doesn't move, but we get exactly the 8 symmetries of the squares, the 8 different ways you can pick up a square and put it down in the same place. So each of these is a symmetry of the square. And this set you check is closed under multiplication, so it is the group of symmetries of the square. There aren't any others. So this is an extremely interesting problem and worth spending a lot of time thinking about. Okay. That's problem number 3. Sorry, that's problem number 5. That's the conclusion of problem number 5. 4, I decided to skip because it's not as interesting as the others. 3, I did. We still have to do 6, 16, and 17. So let's take a look at that. So we have problem 6. So S is a subset of a group G, and by S inverse, we mean the set of inverses of each element of S. So it's S inverse for all S in S. And we want to show that the group generated by S inverse is the same subgroup of G that is generated by S. So what does it mean? So this is the group generated by S, which is the smallest subgroup of G that contains S. So suppose we let H be this subgroup, and we let, let's say, K be the subgroup generated by S inverse. So S is in H because H is all, it contains all the elements of S. It's a subgroup, it's the smallest subgroup that contains all the elements of S. So that means that S inverse is in H because a subgroup is closed under the operation of taking inverses. And this is true for all S in S. So the set S inverse is contained in H. So H is a subgroup that contains S inverse, and the subgroup K generated by S inverse is the smallest subgroup that contains S inverse, so it's contained in H. Because H is a subgroup that contains S inverse. So H contains the smallest subgroup that contains S inverse. But this argument is symmetric. S inverse is in K, which implies that S inverse inverse is in K. Because again, K is a subgroup and it contains the inverse of each of its elements, but the inverse of S inverse is S. So that means the whole set S is contained in K, which means the subgroup generated by S is contained in K, which is H. Because again, K is H is the smallest subgroup that contains S, and K is a subgroup that contains S. So H is contained in K. So we have the two identities, H contained in K, K contained in H. And if you put them together, that's the definition of two sets being equal. And that's the end of the proof. Let's look at the remaining two problems. Number 16, we have the symmetric group Sn, which is the group, this is the symmetric group of permutations of the set 1, 2 up to n. And we know some facts about permutation. So every permutation is a product of disjoint cycles. So for example, if we take sigma to be, let's say, a permutation of some permutation of S7, say, I don't know, 3, 5, 4, 1, 2, 7, 6. I can write this as a product of cycles. Let's see, 1 goes to 3, 3 goes to 4, 4 goes back to 1, 2 goes to 5, 5 goes back to 2, 6 goes to 7, 7 goes back to 6. So here I have 3 cycles, a 3 cycle, a 2 cycle, and a 2 cycle. So every permutation is a product of cycles. But every cycle is a product of every K cycle. K cycle is a cycle that has K elements in it, is a product of what are called 2 cycles, or 2 cycles, which are called transpositions. That's another word. And in fact, you can get by with K minus 1, 2 cycles. So for example, if you had the cycle 2, 7, 3, 8, 4, that's the product of 2, 7, 7, 3, 3, 8, 8, 4. So here we have a 5 cycle, and here we have 4 2 cycles. And you can check the product of these 2 cycles is this 5 cycle. So the set of 2 cycles, all 2 cycles, generates the symmetric group Sn. If you look at all the 2 cycles, 1, 2, 1, 3, 1, 4, up to 1n, 2, 3, 2, 4, up to 2n, 3, 4, and so forth, all of the 2 cycles, the smallest subgroup that contains all of the 2 cycles is the entire group, the entire symmetric group, Sn. Okay. So this we already proved, and in problem 16, we want to show a certain subset of the 2 cycles is in fact enough to generate the whole group. So problem 16 is to show the symmetric group Sn, where n greater than or equal to 2, is generated by not necessarily, you don't need all of the 2 cycles. It's enough to pick a certain n minus 1 of them by the n minus 1 2 cycles 1, 2, 2, 3, 3, 4, 4, 5, and so forth, up to n minus 1n. So it's just the 2 cycles that consist of not all pairs of integers between 1 and n, but just the pairs of consecutive integers, and they're n minus 1 of them. So, of course, for n equal 2, S2 just consists of the identity and 1, 2. And so this is generated by 1, 2. The smallest subgroup that contains 1, 2 contains 1, 2 in its inverse, which is 1, 2, and it contains the identity, and that's it. So that's pretty easy. Let's look at the case n equal 3. So S3, let's just recall, it consists of the identity. There are 3 2 cycles, 1, 2. Well, okay. 1, 3, and 2, 3. And there's the 3 cycle 1, 2, 3, and the 3 cycle 1, 3, 2. That's what the group S3 is. And we know that S3 is generated by just the 2 cycles, 1, 2, 1, 3, and 2, 3. Well, we have to show, this is, in this case, we must show that S3 is in fact generated by 1, 2, and 2, 3. These are the 2 2 cycles that consist of consecutive elements. So, but we know S3 is generated by these 3 transpositions, 2 cycles. So if we can show that somehow we can write 1, 3 as a product of 1, 2, and 2, 3, we're done for the case n equal to 3. So how can we show that? Well, if I take 1, 2, 2, 3, and 1, 2, this is in the subgroup generated by 1, 2, and 2, 3. But what is this? This sends 1 to 2, 2 to 3, 3 to 3. So 1 goes to 3. 3 goes to 2, goes back to 1. And 2 goes to 1, goes to 2. So, in fact, 1, 3 is this product. So 1, 3 is in the subgroup generated by 1, 2, and 2, 3. So if I just take the transpositions 1, 2, and 2, 3 and look at the subgroup they generate, that contains 1, 3. And if it contains 1, 3, then it contains all the transpositions in S3. So it generates S3. So if H is the subgroup generated by 1, 2, and 2, 3, then what I just showed is that 1, 3 is also in H. And so H contains all transpositions. So H equals S3. So that's the special case n equals 3. And the hard work is to prove this for all n. So again, just to get an idea of what one might do, let's look at the next case. n equal 4. So n equal 4, we have S4 is generated by all the transpositions 1, 2, 2, 3, 3, 4, and 1, 3, 2, 4, and 1, 4. These are all, there's 6 transpositions. There are 6 ways to choose 2 elements from 1, 2, 3, and 4. And I want to let H be the subgroup generated just by the transpositions, which are consecutive elements. So I have to show that each of these transpositions can be written as a product of 1, 2, 2, 3, and 3, 4. So let's do it. Let's see. I take one. Now, how do I know how to do this? Because I spent a lot of time working this out before coming online to record this lecture. There's a lot of work involved. So it's a lot of just playing around with paper and pencil, a lot of paper and a lot of time to see what to do. So if you experiment a little bit, you might see that if you take 1, 2 times 2, 3 times 1, 2, what is that? 1 goes to 2 goes to 3. 3 goes to 2 goes back to 1. 2 goes to 1. That's the transposition 1, 3. So 1, 3 is in H. That's this guy. What about 2, 4? So if I take 2, 3, I want to get 2, 4 in there, right? If I take 2, 3, how can I do this? Let me think for a second. Let's say I take 2, 3, 3, 4, and 2, 3. This sends 2 to 3, 3 to 4, 4 to 4. So 2 goes to 4. 4 goes to 4, goes to 3, goes to 2. 3 goes, that's 2, 4. So that's an H. So I can write each of these as a product of these three, as a word, if you like, in these transpositions. And what about 1, 4? So I have 1, 2 is in H. I just proved that 2, 4 is in H. So let me do 1, 2, 2, 4, 1, 2. What is this? This sends 1 to 2 to 4, 4 to 2 to 1, and 2 to 1 to 1. That's an H. So all of these 3 permutations, these 2 cycles or transpositions are in H. So H contains all 6 2 cycles. Therefore, H is equal to S4. Okay. How do we prove this in general? So that n be, let's say, greater than or equal to 5. And it's already considered 2, 3, and 4. How do we prove that the subgroup generated by all the 2 cycles, k plus 1, where k goes from 1 up to n minus 1, is in fact the whole symmetric group. So every 2 cycle is of the form. So if you have a 2 cycle, you have 2 numbers. Let's say k is the smaller, and the larger one I can write that say is k plus r for r going from 1 up to the biggest k plus r can be is n, up to n minus k. So we have all of these 2 cycles. Now, for r equal 1, k plus 1, that 2 cycle is in H. What about for r equal 2? So I want to show that every cycle k plus 2 is in H. For k going from 1 up to n minus 2. So if I take k plus 1 and multiply it by k plus 1, k plus 2, and multiply it by k plus 1. So each of these is a 2 cycle where the terms just differ by 1. So each of these is in H, which means this product is in H, because H is a subgroup, it's closed under multiplication. So this sends k to k plus 1, k plus 1 to k plus 2, k plus 2 to itself. K plus 2 goes to k plus 1 goes to k, and k plus 1 goes to k plus 1. So this is this transposition where the difference of these numbers is 2, k and k plus 2, for all k. So this is an H for all k. So every transposition where the 2 numbers differ by 2 is in this set. So now we can do a kind of proof by induction. Let R be some number between 1 and, let's say, n minus 2. Suppose all the transpositions k plus r belong to H for all r going from 1 up to n minus k. So all the 2 cycles where the 2 numbers differ by r belong to H. And I want to show that we can get all the transpositions where the 2 numbers differ by r plus 1. I want to show this is an H for all k going from 1 up to n minus k minus 1. N minus r minus 1. So let's write the following. We know that k plus 1 is in H. And we know that k plus 1, k plus r plus 1 is in H, because these numbers differ by r. And our induction assumption is that all of the transpositions where the 2 numbers differ by r are in H. So therefore, k plus 1 times k plus 1, k plus r plus 1 times k plus 1 is in H. But if you follow what this is, what is this? K goes to k plus 1, goes to k plus r plus 1. K plus r plus 1 goes to k plus 1 goes to k. And k plus 1 goes to k plus 1. This is in H. So this transposition where the two numbers differ by r plus 1 is in H. And so we're done. We proved that if H contains all transpositions where the numbers differ by r, then it also contains all transpositions where the numbers differ by r plus 1. So inductively, this contains all transpositions. Now we're done. We're done. Again, there's a lot of algebra here, abstract algebra and very concrete computational algebra. And it's instructive to spend time on trying to understand permutations and understand what goes into these proofs. Okay, it's a hard problem. What about number 17? Now this is even harder. Show that the symmetric group Sn for n greater than or equal to 2 is actually generated by just two permutations. The simple transposition 1, 2, and the n cycle 1, 2, 3, 4, up to n. So the smallest subgroup of Sn that contains these two particular permutations contains the whole group, is the whole group. And why is that? Of course, in the case n equal 2, this simply says S2 is generated by 1, 2, and 1, 2, and S2 is just the identity in 1, 2, the transposition. So that's certainly true. What about for n equal 3? We want to show S3 is generated just by the transposition 1, 2 and the cycle 1, 2, 3. So any subgroup that contains just these two permutations must contain every permutation. Why? Why is that? So let's do it sort of just by calculation first. We know that, so suppose we let H be the subgroup generated by 1, 2, and 1, 2, 3. So then the inverse of the permutation 1, 2, 3, which is the permutation 3, 2, 1, is also an H. And let's do an experiment. Suppose I calculate 1, 2, 1, 2, 3, 1, 2, 3, 2, 1. Just for fun. Let's see what happens. So if you trace the trajectory of the element 1, this sends 1 to 2. This sends 2 back to 1. This sends 1 to 2. And this sends 2 back to 1. So 1 goes to 1. What about 2? 2 goes to 1. 1 goes to 2. 2 goes to 3. And 3 goes to 3. So in this permutation, 2 goes to 3. What about 3? 3 goes to 2. 2 goes to 1. 1 goes to 2, 2 goes to 1. So 3 goes to 1. Something's not right about that. Let's see. 3 goes to 2, 2 goes to 1, 1 goes to 2, and 2 goes to 1. That's correct. 1 goes, oh, sorry, I did this wrong. 1 goes to 3, 3 goes to 3, 3 goes to 1, and 1 goes to 2. So 1 goes to 2. Let me think for a second. Yeah, this is correct, but let's just write down what it is, but it's not what I really want. So if I take 1, 2, 1, 2, 3, 1, 2, 3, 2, 1, I'm going to get a 3 cycle. 1 goes to 2, 2 goes to 3, 3 goes, 1 goes to 2, 2 goes to 3, 3 goes back to 1. So this is correct, but not interesting. Let me do it slightly differently, and it'll work nicely. So again, we want to show the subgroup generated by 1, 2, and 1, 2, 3 is all of S3. So for example, we know S3 is generated by all the transpositions, 1, 2, 2, 3, and 1, 3. So let's say that H is the subgroup generated by these two permutations. So if I take, so 1, 2, 3 is in H. So the inverse of 1, 2, 3, which is 3, 2, 1, is also in H. And if I take 1, 2, 3 times 1, 2 times 1, 3, 2, this is a product of permutations in H. So this is also in H. But what is this equal to? 1 goes to 3. This sends 3 to 3. This sends 3 back to 1. So 1 goes to 1. 2 goes to 1, goes to 2, goes to 3. So 2 goes to 3. 3 goes to 2, goes to 1, goes to 2. So 3 goes back to 2. So the permutation 2, 3 is in H. So if I take 1, 2, 3, 2, 3, 1, 3, 2, this is also an H. But let's compute this permutation. 1 goes to 3, goes to 2, 1 goes to 3, 3 goes to 2, 2 goes to 3. So 1 goes to 3. 3 goes to 2, goes to 3, goes to 1, so 3 goes back to 1. And 2 goes to 1, goes to 1, goes to 2, so 2 is fixed. So 1, 3 is an H. So H contains all the transpositions. 1, 2, 2, 3, 1, 3. So H is all of S3. So that's the case, H equal to 3. So let's try to prove the problem in general. So we want to prove if we let H be the subgroup generated by 1, 2, and the transposition 1, 2, and the n cycle 1 up to n, that this is actually equal to Sn. That's what we want to prove. So let's say that we let sigma be this transposition, this permutation, and sigma inverse just reverses it. So n goes to n minus 1, goes to n minus 2, goes to 3 to 2 to 1. That's sigma inverse. So let's compute. So if I take 1, 2 times sigma, times 1, 2 times sigma inverse, this is an H. And what is this permutation equal to? So this is 1, 2, 1, 2 up to n, 1, 2, and down to 1. So let's just trace some of the elements. 1 goes to n. This sends n to n. I'm assuming now that n is at least 4, because I already handled the cases 2 and 3. So 1 goes to n goes to n goes back to 1, and 1 goes to 2. So 1 goes to 2. What about 2? Let's see, 2 goes to 1, goes to 2, goes to 3, goes to 3. So 2 goes to 3. What about 3? 3 goes to 2, 2 goes to 1, 1 goes to 2, and 2 goes to 1. So 3 goes back to 1. And suppose I take any number r from 4 up to n. So I take that number r goes to r minus 1. R minus 1 is at least 3, so it's not moved by this transposition, 1, 2, goes to r minus 1. This sends r minus 1 back to r, and this keeps r fixed. So r goes to r. So in fact, this permutation is equal to 1, 2, 3. So 1, 2, 3, that 3 cycle is in H. And what was the calculation that we did before? We saw that, so we have 1, 2, 3 is in H. But then before, in the previous problem, or in the previous part of this problem, we saw that 1, 2, 3 times 1, 2 times 1, 3, 2 is equal to 2, 3. So the transposition 2, 3 is in H. So let me do the following calculation. 2, 3 sigma 2, 3 sigma inverse. What is that equal to? So this sends 1 to n. Sigma sends n to 1, so sigma inverse sends 1 to n. N's at least 4, so n goes to n. This sends n to 1, and this sends 1 to 1. So 1 goes to 1. What about 2? 2 is sent to 1, is sent to 1, is sent to 2, is sent to 3. So 2 goes to 3. 3 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 4. So 2 goes to 3, 3 goes to 4. What about 4? 4 goes to 3, goes to 2, goes to 3, goes to 2. So here we have a little cycle. 2 goes to 3, goes to 4. And if I take R, any number from 5 up to n, R would go to R minus 1, goes to R minus 1, goes to R, goes to R. R is fixed. So 2, 3, 4 is in H. And if 2, 3 and 2, 3, 4 are in H, 2, 3, 4 times 2, 3 times 4, 3, 2 is also in H. And this permutation sends 2 to 4 to 2, 3 to 2 to 3 to 4, and 4 to 3 to 2 to 3. So 3, 4 is in H. And if 3, 4 is in H, I just iterate this operation. And what is the operation that I am iterating or repeating? It's the following. We have sigma is 1, 2, up to n. And sigma inverse is n down to 1. If I take R plus 1, that transposition times sigma, times, again, R plus 1, times sigma inverse, what is that? So suppose I take a number k, which is less than or equal to R minus 2. Right. So this sends k to k minus 1. K minus 1, actually I can go up higher because I want k minus 1 to be less than or equal to R minus 1. Yeah, that's right. So k minus 1 is less than or equal to R minus 1. So k minus 1 gets sent to k minus 1, gets sent to k, gets sent to k. So k is fixed between 1 and R minus 2. Suppose I take R minus 2. Let's see what happens. R minus 2, sorry, and k up to R minus 2. Suppose I take R minus 1. So R minus 1 gets moved down to R minus 2. Goes to R minus 2, goes to R minus 1, goes to R minus 1. So that also doesn't move. What about R? So R goes to R minus 1, goes to R minus 1, goes to R, goes to R plus 1. So R moves up by 1. R plus 1 goes to R, goes to R plus 1, goes to R plus 2, goes to R plus 2. So R plus 1 goes to R plus 2. So when this R goes to R plus 1, R plus 1 goes to R plus 2. What about R plus 2? R plus 2 goes to R plus 1. R plus 1 goes to R. R goes to R plus 1. And R plus 1 goes to R. So R plus 2 goes back to R. So that's a 3 cycle. And what about the numbers bigger than R plus 2? So if R plus 3 less than or equal to k less than or equal to n, this number k goes to k minus 1, goes to k minus 1, moves up to k, goes to k. So k is fixed. So this is in my subgroup H. And if r plus 1, and r plus 2 is in H, and r plus 1 is in H, what was our previous calculation? So if this is in H, r plus 1, r plus 2 times r plus 1 times the inverse of this, r plus 2, r plus 1, r. We calculate what happens, what permutation this is. R goes to r plus 1, goes to r plus 1. Double check. R plus 1, r plus 2, r plus 2, r plus 1, r plus 1. This sends r to r plus 2, r plus 2 to r plus 2, r plus 2 back to r, so r doesn't move. But r plus 1 gets sent to r gets sent to r plus 1, r plus 1 gets sent to r plus 2. R plus 2 goes to r plus 1, goes to r plus 1. We get this transposition. So r plus 1, r plus 2 is in our group H. So H contains 1, 2. So we saw it contains 2, 3. So it contains r plus 1, but then it contains r plus 1, r plus 2. So H contains all pairs of consecutive transpositions. And by the previous problem, H is equal to all of Sn. And that, lo and behold, is the proof. Again, algebra is not supposed to be hard or easy, but there's a lot to it. And there's a lot of interesting theoretical and practical uses of permutations. And this is a very good exercise, worth spending some time, and time means hours actually, thinking about this and looking at examples and seeing how everything works. That is the end of homework 10. Bye.